ACM Coimbatore Professional Chapter Meeting and Tech Talk. I'm very happy to welcome and introduce two very young, vibrant researchers, Professor Swaprava and Dr. Rohit. So maybe 1 minute I can talk about them, sir? 1 minute. Yeah. Yeah, sure. So just to introduce them, Soprava Nath is an associate professor of the computer science and engineering, IIT Bombay, and he is also affiliated with the Center for Machine Intelligence and Data Science and Trust Lab at IIT Bombay. Previously, he was in IIT Kanpur and did fellowships, postdoctoral fellowships at Carnegie Mellon University, Pittsburgh, and ISI, Indian Statistical Institute, New Delhi. And of course, he's a PhD from the IAAC. And I also have Dr. Rohit Vaish, who's an assistant professor in the Department of Computer Science and Engineering at IIT Delhi. He's also part of the Yardi School of AI and Theoretical Computer Science group at IIT Delhi. He was formerly a postdoctoral researcher at TIFR and Rensselaer Polytechnic, which is upstate New York. And he's also a PhD from IAC, so they share a common connection. And they work in the intersection of computer, algorithms, economics, and very exciting areas. So very warm welcome on behalf of the ACM Coimbatore Professional Chapter. I also welcome, the host is Dr. The host is our mentor, Professor R. Nadarajan, who's the director of this institute, Dean of Placement, and he's the mentor to many people in the computer science area in this part of the country. Also former ACM Coimbatore chair. And of course, Dr. Ranga Rajagopal, Ranga, hello, Chief Operating Officer of ACM. I'm sure you have been in touch with him a lot. And he also used to be the chair of the Coimbatore chapter. So again, welcome to Coimbatore, and I hope the students have a very exciting time interacting with them. Thank you so much.
Okay. Yeah. Okay, thanks for the very kind introduction, and I'm delighted to be here. And sorry for all of you to keep you waiting. The topic that we are going to talk about is essentially our areas of interest that lies at the interface of economics and computation. At this point, you might be wondering what is the connection between them. I will try to give you some examples, and feel free to stop me at any point. You can ask me questions at any point if things are not clear, because the purpose is not to give you a lot of information, rather to ask you and keep you thinking about the problems that we present. So as the title suggests, that here we will be talking about algorithms and also about self-interest. Let me try to give you some examples so that you can understand what we mean by this self-interest. So let's say there are two neighboring states, and one of them has a king who is actually making decisions for that state. On the other hand, the other state has a queen. Now, it's an ancient time, and there are very simple strategies that you can do. let's say they are thinking about whether they should invest more on agriculture or invest their whole effort and money on agriculture, or they therefore coming up with new techniques of cultivation, or maybe high quality seeds, or they should focus on warfare, therefore designing better war techniques and so on. Now, the thing is that when both of them choose agriculture, so you can clearly understand that what we mean by this matrix, this player, which we'll refer to as the row player, this player, and this player as the column player, these are their choices for the column player, and these are the choices for this row player. When both of them are choosing agriculture, maybe they will solve their food needs, and they are well protected. So both of them are significantly happy. We are going to denote their happiness with this number called 5. It doesn't matter what is its unit, because we will be only talking about the relative comparison. It can be 500 rupees, 5,000 gold coins, or whatever unit you put in, it's the same for all of them. Now, if both of them are going for war, you can think of that there will be a very fierce war, and people will lose their life, lose properties. Even though they are able to defend their own countries or own state, the outcome will not be as nice as both choosing agriculture, right? It will be much smaller, so which we are going to denote with 1. So again, the units do not matter, the relative comparison with these numbers is what matters. But the interesting thing happens when one chooses war and the other chooses agriculture. Let's say the country which is choosing war will actually win over, because the other country chose agriculture. They did not develop their war techniques, or they were not prepared for a war, and therefore they will actually lose all their agricultural produce and possibly a loss of life. So the country, like in this case, in this context, the row player who chose war, it will not only get the agricultural produce, maybe it will also get all their land, people, all these things. So their happiness is actually more than the happiness that they were getting in the agricultural context, right? So these numbers make sense. Okay. So and the correspondingly opposite thing happens when the column player, or the king, is choosing war and the queen is choosing agriculture. It's this tuple. So these numbers here mean there are 2 entries. The first entry denotes what is the happiness of this player, and the second entry means what is the happiness of the second player. So that is common in all these cases. Now, if you are the queen, so think about yourself. If you are the queen and your objective is to maximize your happiness, this numbers is what you are willing to thinking about maximizing. What choice would you have made? Agriculture? Why? So for instance, let's say if we have, okay, so the question is the following, so this is what I have already explained. Now, suppose your, the column player, or the king has chosen agriculture. What do you think you should do if you are the queen? So this first entry in this tuple tells you what is the happiness that you are getting, and the second entry is for the other player. But you don't care, so you are self-interested. Imagine that you are self-interested. You only care about yourself, not care about the other country, which happens in conflict situations. So, and the decision has to happen simultaneously. You cannot change depending on what has happened to the other, whatever has been chosen by the other. But in this case, if you assume that this player has chosen agriculture, then what should be your best response? War. Everybody is on board with this, right? Why? Because you are getting this change. So if you look at these 2 numbers, your utility increases if you go in this way. So your happiness increases if you go in this way. What happens if your opponent chooses war? again choose war, right? So does it explain something that you see all the time? The countries are always going for war rather than going for something which is more peaceful. And this game is symmetric. If you just change the same argument for the king and assuming that the queen chooses agriculture, then your utility will be higher if you choose war because that is going to give you. Now you will be looking at row-wise and the second entries in each row. And therefore, what we call this kind of a strategy is what is known as a dominant strategy. No matter what your opponent is doing, whether the opponent is choosing agriculture or war, it's always best for you to choose war. It's called a dominant strategy. And therefore, because both these players are actually choosing war, that turns out to be what is known as an equilibrium. It's a simple outcome. Think about in physics, you have an equilibrium point where nobody would like to deviate, right? So equilibrium is somewhere, even if you push it slightly, it comes back to that point. So this is exactly that in a social setting. Okay, so that's what we understand now. But what do you think is the collectively best thing? The agriculture from agriculture. So there is the irony, even though if they could have actually decided together, they could have chosen agriculture, both of them, and both would have been much happier than this situation where both of them are choosing war, where their utility is 1,1, right? So this kind of a thing we will see the equilibrium outcome. So equilibrium is different from what is the socially optimal. So that's kind of a little not so easy to think about. So let me give you one more example, and then we'll get into how we can design societies. So the whole idea is about designing algorithms in the society so that certain good things happen. So here I like to give the example of going from your hostel blocks to the lecture halls. So let's say your hostel blocks are all located at A, and your destination is your hostel blocks are at A, and your destination is your lecture hall. And there are two possible ways of reaching to your lecture hall. And let's say there are 100 vehicles, 100 bicycles. Let's say you are taking your bicycle. There are 100 people. They all want to go to the lecture hall, and there are two different paths. Now these paths have certain path costs. So that how much time it takes for you to reach from A to B or B to D. These are the things that you have. So A and B, let's say the path AB. So the path AB and CD are congested lanes. So what it means, what 5N1 means is that N1 is the number of vehicles which are moving on this path, and if there are more vehicles, then a narrow lane will get easily congested and it will take longer time to reach to your destination. So AB path is proportional. The time taken for every vehicle to move from A to B is proportional to the number of vehicles that is moving on that path. So it is 5 of N1, and similarly N2 is the number of vehicles which is moving on CD, and that is proportional to that number, so 5N2. While AC and B are wide highways, it does not matter how many vehicles are moving on that path, it will still take a constant amount of time, which is 600 units. Okay? Let's say seconds or minutes, whatever. Now, if you are the first, so again, every individual, every bicyclist is trying to minimize the time to reach to your lecture hall so that you can sleep longer in your hostel blocks. So, which path should you think that 600 vehicles will take? So if you are the first bicyclist who is taking your bicycle out and starting to go to your destination, which path should you take? Any of them, right? So yeah, that's a good answer. So it doesn't matter whether I go in this way or that way, everything is same. So seeing that he is the first person who is actually taking AB path, let's say without loss of linearity, assume that he has started moving on this ABD path. The second bicyclist, what should he or she do? Take the other path, right? The third one? Any one of them, doesn't matter. Fourth one? So everybody will try to divide it. So what do you think will happen in the equilibrium?
It will be stable if everyone observes what the other one did.
Right, so I want, so how will this 100 vehicles will get split?
50-50.
50-50 will go in those 2 weeks. Okay, so you see what is the, so this is an equilibrium, and can anyone guess what type of an equilibrium this is? I mean, is it, so for instance, suppose this 50-50, one of these vehicles are actually going in this ABD path, one more, let's say 51 and 49, right? So then that the one extra bicyclist who is going in that ABD path should actually change its position. So this is a little weaker type of an equilibrium. I have not defined it, so let's not worry about it. But this is a kind of a little weaker type of an equilibrium. So on it. So tell me, what is the amount of time that each vehicle takes now? 50 vehicles who are going in this path, 50 vehicles are going in this path.
850.
So 600 plus 50 into 5, which is 850, right? So remember this number, that how much time each of these vehicles are taking. Now suppose the transportation authority or the institute administration decided that we will actually alleviate this problem. They're taking too long time, so we'll actually add one more path into it. Okay, so let's say this is such a nice path that it takes almost negligible time corresponding to other places. It's like a teletransportation device. The moment you are in B, you are in C. Okay? So now you can tell me the same thing. What should you do if you are the first bicyclist? Which path should you take? Say that a little loudly. ABCD is the cheapest path now. So second vehicle? Again ABCD. Let's say 99 people have taken ABCD. What would be you are the 100%. What should be your move? Still ABCD, right? So what happened suddenly? So everybody has started taking this ABCD path, right? What is the total time taken by each vehicle? So now the equilibrium is that all vehicles are taking ABCD, and the situation actually became worse, right? And this is not a toy example. This kind of a situation has actually occurred in real transportation networks, where people had to actually demolish such kind of BC paths, even though they are very nice, in order to maintain. So you see that the resource is being wasted for B to D because nobody goes there, and similarly for A to C. So this is not the optimal design. So design is very important. This is what I want to impress upon. If you don't take care of the self-interested parts of people who are taking their decisions, your algorithms are not good enough. You can end up in a situation where you have actually made the transportation network or transportation situation even worse. Okay, so now talking about how can we design society, I'll take so I have about 15 minutes. So now let me try to motivate the problem so now I see the reason why we want to design systems, and our objective is to design algorithms which will give you a better societal outcome. What is a better societal outcome? We'll soon see. We'll have to have some axioms, and then we'll show that this kind of a thing can actually be designed, but even if you have self-interested people, the good things can still happen. So let's think about dividing a cake. It's a metaphor for many other things. Cake is something like something that we all like, and we want to do it fairly. We have not defined what is fairness, but we will define it formally. But what is the property of a cake? It has 3 properties. The first thing is it's heterogeneous. Different parts of the cake is of different type. Maybe some part has chocolate, some part has vanilla, some part has something else, some part has the cherry on top. So you like different parts of this differently. So the equal amount, even if I give the same amount, or maybe same, let's say 500 grams of this cake, different 500 grams are valued differently, right? So you don't like that. So suppose you do not like chocolate, then that chocolate piece is not worth it. So you like the vanilla piece, that is more worthy to you. So everything is about how much you like this piece. So that is heterogeneous. Different parts of the cake has different values for you. It's perfectly divisible. You can make as fine cuts as possible. That's something, any fractional allocation is feasible. And the third one is you have different preferences for it. That means even if I show you, so maybe you like chocolate a lot, I don't like it. So even if the same piece is valued differently by you than me, right? It always happens that you like chocolate, but your friend doesn't like chocolate, right? So the same piece may have different values for different. So with this setup, we are now going to do a fair allocation, right? So fair division of this cake. And how do we define fair division? So for all purposes, we'll be assuming that the cake is a line, because you can always think of a knife which is starting from the center, and you are rotating that knife. So wherever you stop it, that piece is actually the piece that you get. You can ask what is the value for that, and that's how we are going to define it. So, 0 to 1 is like, and you may have different value. So what this three properties mean is that you may have different valuations for different parts of this cake, and the different people may have different valuation distributions over it. So, and we are going to assume that for every player, the total cake is valued 1. This is just for normalization. That how can we actually compare one person with another if the cake's valuation itself is different for different people. So now we are going to define what is fairness. So there are two very common notions of fairness. The first common notion is proportional division, which means that I give you a piece, and you look at the entire cake, and you think you have got at least average. So let's say n are the number of people. Imagine that there are only 2 people. Then you want to have a piece which is valued at least half by you. Then you can say that, okay, I got at least half, more than the average. Then I think that this is a fair division. And the other player also thinks the same way, right? So this kind of a allocation is called proportional division. This is one objective for us. The second is what is known as envy free. So I look at my friend's piece, and so AI is the piece that I get, AJ is the piece that my friend gets, and I look at the value of my piece versus my value for the other agent's piece, right? So I look at someone else and I think, oh, this is much better, so then I become envious. If that does not happen, that means I like my piece better than my friend's piece, then I'm not envying my friend, so that is, I'm envy free. If you can actually make it for every possible pairs of agents, I and J, then we are going to call that division as an envy free division. Rohit will talk much more about it, about this type of envy freeness and the ideas of fairness. Now, my question is that, how many of you have siblings? So this kind of a cake cutting problem you have encountered in every birthday, right? So what do you think is a fair division, which is like either you do not envy your sibling, or you at least know that you got half of it? What type of things that you actually did in order to do a fair division? No, but how did you do it? So my question is how you can actually do such kind of a, how do you cut this cake? I give you the total cake, and you and your sibling is trying to, assuming 2 siblings. So you are trying to divide this cake so that you don't envy your the other siblings, and also the other person also does not envy you. How can you actually come up? What are the techniques that you have done?
Usually mom splits it up for me.
Mom splits it up, but mom does not know how what is half for you, right?
Yeah.
That's a difficult problem.
If we show our dissatisfaction and
then she will again give some more piece.
Yeah.
Okay, so from next birthday onwards, maybe you can apply this technique, which I call the I cut you choose algorithm. What is it? You ask one of these siblings to cut the cake, and ask that who has cut the cake to choose second, not first. So the other person who is standing there, he or she will pick the first piece. Do you think that will satisfy these properties? Will that be envy free? Why?
They have their contribution to what they have to decide.
Can you be a little more specific? So when the first agent is cutting the cake, what is he thinking?
He'll get a bigger or better portion for him.
But he doesn't know. He picks second.
Yeah. So all you know is he can't contributed something so that would not.
Contributed as in?
I guess, sorry.
Yeah, go ahead.
When I choose to cut the cake, I will be thinking what would they think.
What will be the worst case scenario?
Yeah.
So you might get the smaller piece.
They'll try to get the bigger. If I cut the cake like 0.2 and 0.8, obviously the next person gets to choose it. So
Yes.
they might obviously choose 0.8.
Well,
Since I don't want
these
to do
two
that,
different people may have different values for the same cake.
But I'll be trying my best. They try to choose 0.8. So
Okay.
I can't have an option for them to have 0.8. Like I
Okay.
tried my best to split it fairly
Fairly, as in?
for everyone.
Okay, so what will be that number instead of 0.2, 0.8?
0.5.
0.5, okay? So you try to cut the cake exactly half in your view. That might not be the same as your siblings' view, but you are happy because you got at least half of the cake, right? Whichever piece your sibling picks, you get half. That is precisely the principle why it is envy-free. Right? So the other agent is also happy because if the second person who is choosing finds that one of these pieces is larger, he will pick it and will be happy because he will not envy the other piece. You, as a cutter, will not envy any of this because you are indifferent between those two things. Okay, so I cut, you choose algorithm actually satisfies, and I will not get into the details. There are extensions of this when you have more than two siblings. That thing becomes much more complicated. So this is half and half when the cutter is cutting. This might not be physically the half point, because maybe some part of this has chocolate and I don't like it. Then I'll cut the piece such that it is exactly half. Whichever piece I like, whichever part I like, I will cut that in half. If I like the cherry on top, I will cut the cherry also in half. Okay, so that's the idea. And now so the idea is that this will see that this is proportional as well, because it is actually giving at least half to each of these players, and it is also envy-free. So this works for two agents. Yeah, so 3 agents and more is possible to do, but it's much more complicated. So let's move on. So there is another type of mechanisms which is known as auctions. So here also our objective is to, let's say, sell this object. So there is an auctioneer who wants to sell this object, and there are multiple individuals who are willing to bid for this object, willing to purchase this object, but they have different happiness or different valuations associated with it. If they get this painting, maybe the A3 has much higher value. We are talking about their true valuations. This is something that is inside their head. You might not be able to see it as an auctioneer. You'll have to somehow elicit this information from them in order to give do a better allocation. And what is a good allocation? So I want to give it to the agent who really values it the most, and that is, like in this case, this third agent, I want to give him, but I do not know this value, so how do I actually design a scheme such that they voluntarily reveal their valuations in a truthful manner? Okay, and of course every individual is trying to get this painting and get their value, but they also want to minimize their payment. Nobody wants to make a larger payment. The minimum amount of payment at which you will get this item is what they're looking for. Okay, so the setup is clear. Now what is a good way of doing it? You can ask everyone to bid, but there is a twist. You give the item to the highest bidder, he will win the object, but that will pay the second highest bid. So this is something which is not so easy to think about. So why is it the case? So if you think about this, so let's say this is the level, and let's say the first agent is trying to misreport. Okay, so let's say this auction is known as the second prize auction, and we are going to claim that the agents will be truthful regardless of what other agents are doing. Okay, so let's say the agent 3 and agent 2's reported value is as shown in the picture. Now agent 1 is thinking about whether I should increase my bid or misreport my bid, or increase or decrease than my true value. Okay. So suppose Alice, she actually reports a value which is actually larger than the value 3. So in that case, she will win this object, of course, because she is the highest value. According to this rule, you will have to give it to her. But the real value for this object, which she really pursues, so let's say this painting is valued 100 rupees to to this player, that is not going to change based on her report. Her report can be anything, but she really values it 100. But now how much she has to pay? Second highest bid, which is here, right? So she really values it at this point, and she is actually paying this, which is worse, right? So negative. If she had reported it truthfully, then she would not own it, but she would have at least got 0 value, not a negative value, negative utility. Sorry. Press something wrong. Okay. Now, yeah. So that is the case. And similarly, you can think that if he reports low, then there could be a situation, all shown by these dotted lines. If that is that was the report, she could have owned this object, but she actually reported low. There is a risk that she will completely lose this object, which is worse than reporting untruthfully. So we're actually trying to give you a kind of a pictorial proof of why that claim is true. No matter whatever the other people are reporting, it's always better to stick to your true report, true value, rather than misreporting it. Okay. All right. So let me just try to connect. Let me just skip this slide. Where it falls in this the whole view of artificial intelligence, because that's not our objective for today. Yeah, so this rational action is actually one part of artificial intelligence, which deals with this area called game theory and mechanism design. So if you want to summarize all these previous things, so in our context, we will be defining a game as an interaction between agents who always want to maximize their utilities, and the type of guarantees that we give, that these are the paths that they will choose, or this is the actions that the kingdom and the queendom will choose. That is a predictive approach, and that is what game theory is all about. And on the other hand, when we came to this fair division problem or the auction problem, we actually designed the game. So what are the protocols of this game? Or what should be paid by every agent, such that certain desirable outcomes happen. And this is a prescriptive approach. So these are two complementary techniques. One is a predictive approach, giving guarantees given a game, and the other prescriptive approach, how should we design it such that certain desirable outcome happens. And there are many applications. Every time you type something on Google or Facebook, you are actually watching certain things or maybe looking at certain. So you are looking at certain things. Google is actually, so if you have looked at, maybe this experience has happened to you. So you have purchased a ticket, let's say from Coimbatore to Chennai, and your email, so whenever you open your Gmail, you see advertisements about, let's say, hotels in Chennai, or some other options, take a taxi in Chennai. So how does Google know it? Because it actually mechanically reads your email, and when you have created your free Gmail account, you have actually agreed to all these terms and conditions that your data will be actually used by Google for advertisers. So all those advertisers who are actually showing those taxi ads or hotel ads, they are going to pay a certain amount of money to Google as soon as you click on one of their ads. So this is called the online advertising. It's a $1 billion industry. Same thing happens with Facebook. As you scroll up, all the things that you have watched, they are actually looking at your data and suggesting you certain similar kind of products. So this is a good application of mechanism design. Stable matching, where students are matched with universities or doctors are matched with hospitals, is a very interesting application domain. Organ exchanges is a very important, not so much in India, but definitely much more principled approaches in several other parts of the country. Federated learning, peer grading, airline scheduling, and many more applications where you can use mechanism design. So I'll just like to conclude. I'll just want to say that if you want to probe a little bit more, there are lecture videos and also this lecture notes, the course web pages. There are lecture videos available, so you can actually self-teach yourself about mechanism design and game theory. Generally, you can do some fun reading about Nash equilibrium. Brace paradox was this transportation network that we spoke about. I'd conclude with my group at IIT Bombay, which is known as the Computational Economics Group. There are plenty of people who are members of this, so many students, PhD students, master students. It's an interesting place to work, and I'm very happy that I could actually work with many of the students. So let me just stop at that point. If you are interested, happy to answer your questions. You can send me emails. But please do read. There is in my webpage there is certain open letter written for the interested research students. So I'll stop at that point, and with 3 minutes late to follow it. Okay, thank you.
The loss is an actual loss because personally static your values end up increasing. The ultimate goal is always to win. The loss because human use there's a chance that he could pay for it.
Sorry, so does anyone here have an HDMI to USB-C converter?
Huh?
HDMI to USB-C port.
USB-C.
Okay, I got it. Oh, you got it? Okay. Sorry for the delay.
So it's a negative
Alright, okay. So first of all, thank you all so much for being here. I know it's a Friday evening and I'm probably standing between you and dinner. So we'll try to keep it light. Basically no technical discussion. We'll try to keep it at the level of puzzles and stories. Okay. Before I get started, just a show of hands here likes maths and proofs. Okay, a few of you. Who here hates maths and proofs? It's okay. You can raise your hand. No one hates proofs? Okay, good. I guess I'm the only one. Okay, never mind. I also like proofs. Basically what I want to talk about is this very fascinating area called computational social choice. Okay, there's a couple of terms to unwrap here. Computational referring to computation, algorithms, the act of finding something in a limited amount of time or limited amount of space. And social choice is a subfield of economics, right, which deals with making a choice or a decision for a society. Okay, you make a collective choice for a group of people. For example, when you do voting, right? You elect a representative or a leader based on the choices or the preferences of the electorate or the voters. Okay, so that's an example of a classic social choice problem. In this discussion, I'm not going to focus so much on voting. Rather, I'll talk about a different problem in social choice, which Swaprabha already has touched upon, which is to do with fairly allocating stuff. Okay, all right. And you know, the point of presenting this discussion to you is to just get you interested and make you aware of this area, which I feel should be known more broadly. And hopefully you'll see that your interest in mathematics and prose, right, and maybe even algorithm design and computer science ties very well with problems that seemingly have nothing to do with computation. Right? These are economic problems, these are resource allocation problems, these are problems in social sciences, right? But there's a very close connection between these problems and that of computer science and mathematics and algorithms. Okay, so try to be on the lookout for this connection. If you don't see it, please ask me questions. Okay, and please feel free to stop me at any point if anything is not clear. Okay, so like I said, I'll try to keep things light. Okay, so I'll try to start with the puzzle, and I'll try to motivate the area with the puzzle. And this puzzle, like I said, has to do with the idea of distributing some stuff fairly among a bunch of people. Okay, so let's set up some of the background in order to get to the puzzle. Okay, so here's the model I have in mind. Okay, so suppose you have a bunch of agents or people, right? And you have a bunch of items. Okay, now these items A, B, C, D, and E, I want to highlight that these are discrete items. Okay, so unlike in the previous talk where you had a cake which you can cut up anywhere you like, this time you cannot cut up these things, right? So think of a bunch of, let's say, siblings fighting over an inherited property, and this property consists of, let's say, a house, a car, a very valuable painting, a very valuable ring, and so on, right? So you cannot cut up a car and give it to 3 different people, right? It loses its value. So a car must go entirely to one person or the other. It's an indivisible or a discrete object. Okay, so think of each of these things as those indivisible items. Alright, so we cannot cut these things off. Alright, now let's say these siblings, or more generally any sort of people who have these resources, who are interested in these resources, they have some preferences over these resources. Okay, and those are given by this matrix of numbers. So how do we read this matrix? So let's look at, let's say, this red agent here. So this number 2 means that the red agent has a value of 2 for the object C. Meaning if you give C to the red agent, it gets 2 units of happiness. Okay. Similarly, if you give A to red agent, it gets 4 units of happiness, right? So bigger numbers are better, they make you happier. Smaller numbers make you less happy. Okay? Numbers are basically units of happiness. Alright. What we're looking for is a way of dividing these items among these agents such that every item goes to exactly one agent. Okay, so you want to finish up these resources. You don't want to leave anything on the table. And because these are indivisible, every resource must go completely to one of the agents. Right? There's no fractionalness allowed. All good? Everyone understands what is happening? Yeah? Alright, cool. So I have told you how any individual values any individual item. But if you are looking closely, this blue agent is getting a set of items, not just an individual item, right? So how does this blue agent value a set of items? Okay. So for this discussion, I'll assume that whenever you get a set of items, your value for that set is the sum of your values for the individual items in that set. In other words, your value for set is additive. Okay, it adds across the constituent elements. All good? Okay, so now once I give you this information, you know every agent's value for every single subset of items, right? So just as a quick sanity check, suppose I have n items, how many subsets are there? Anyone? 2 power n, right? Exponential number of subsets. So I don't have to give you an exponential number of numbers here. I've only given you n many numbers, and from that you can stitch together this exponentially rich information. Okay, so that's where this assumption helps you. Alright, anyway, let's keep going. So Swaprabha already touched upon what makes an allocation fair. This is a very well studied notion called NV freeness. But let me just remind you of this notion in the context of this discrete items model. Okay, so NV freeness is a property of an allocation, right? It says that an allocation is NV free if every agent prefers what it has over what anyone else has, right? So no one is envious of or jealous of someone else. You are happy with your own life, the other person is happy with their life, no one wants what someone else is getting, okay? Let me just give you a quick example to make sure you understand the concept. So we have, let's say, these two agents and these three items here, and these are the numbers, okay? Suppose I present to you an allocation like this, okay? So that means item A is going to red and B and C are going to blue, okay? So is it an NV-free way of dividing these resources? Yes. How many people say yes? No one says yes? Really? Okay. How many people say no? Okay, the ones who didn't raise hand are in which camp exactly? Okay, so most of you say it's no. Why is it no? Because look at the, yeah, you tell me, why is it not NV-free?
Blue is 6 units of happy.
Yes,
Red
so
is
who
4
envies who?
units of happy. Red envies blue.
Red envies blue. Why does red envy blue?
Blue got more happiness than red.
Sure.
I mean,
But,
the items that blue got, the items that blue got, red doesn't envy the items that blue got. So, according
are
to
you
this,
saying it's envy free or not?
it's envy free.
It's envy free, and what is the reason?
Because the items that blue got, A doesn't envy them. Like according to blue, the items that A got is just value of 3.
May I know your name?
Deshaun Collins. Deshaun.
Deshaun. Okay, so Deshaun is absolutely right. There is no envy here, right? Why is there no envy? Because look at the red agent. Okay, red is getting 4 for what it has, and according to red, whatever blue has, B plus C is of value 3. Yes? So in red's eyes, whatever blue has is of less value compared to what red already has. Red does not envy blue. Yeah? Yeah?
I doubt that's the case because when you look at the broader perspective, it could have a better distribution, right?
Yeah, I'm not saying, so I'm saying, let's say this is given to us. I'm not saying there is no, like there could be other ways which are envious and free. I'm saying, let's say someone has given us this is
what if red got B 2, then the total happiness would be 5 5.
Right. If red got B, that the analysis would be different. I'm saying, suppose let's just analyze this way first, and then maybe I'll get to what you're saying. Do you believe this way of dividing stuff is envy free?
Yeah.
Anyone in the yes camp now? Oh, some of you. Anyone still in the no camp? Change sides. Okay, interesting. Okay, so why did you change sides? Well, because hopefully you realize that, from red's perspective, whatever red is getting is more than what blue is getting. So red does not envy blue. And from blue's perspective, whatever blue is getting is better than what it thinks red is getting. Right? Blue thinks it's getting 1 plus 5, and blue thinks red is getting 1. Right? 6 is bigger than 1, so blue does not envy red. Right? Every agent is happy with what it has. It does not envy what the other person has, hence it's envy free. Okay, now you're suggesting a different way where you give B to red and the others to blue.
Yeah, the C
A and C
blue.
to blue.
No, just C to blue.
Just C to blue and A and B to red. Okay, so if A and B both went to red, red is only getting something extra. It's still happy with its life, right? But what about blue? If blue is only getting C, it still does not envy red, right? Blue has a value of 5 and red has a higher value than before, but it still does not envy red. So that's still envy free. Yeah, so even this other way of assigning stuff is also envy free. Okay, I hope the definition is clear to everyone. Yeah?
It's more equal, but
Any questions about what envy freeness is? This is a good time to ask.
envy free than
Alright, okay, right? So red thinks according to red's value, its bundle is the best. Blue thinks according to blue's value, its bundle is the best. Both agents are happy. This is envy free, right? Life is good. Excellent. We can write the same thing in math. Basically, if you write these as subsets of items, AI is what agent I is getting, the set of items that agent I is getting. If you have n many agents, right? Then this says that value of agent I for what it is getting is at least agent I's value for any other agent K's bundle, right? And this is true for every pair of agents I and K. Yeah, so this is the formal way of writing envy freeness, but really the idea is all good? Alright, okay. What is the problem with this envy freeness? It sounds like a very compelling notion, right? If someone figured out a way of dividing stuff in an envy-free manner, there will be no property disputes, right? All siblings will be happy with what they got. There will be no court cases or anything like that, right? The problem is that you may not always have a division. Why? Well, imagine there are two agents and just one item. Right? Let's say just this phone, and Swaprabha and I are fighting over it, right? Whoever doesn't get it is going to be envious of the other, right? So no matter who gets it, no matter what allocation you pick, there is no envy-free way of dividing it. Yeah? So envy-freeness is a very nice concept if you can achieve it. Unfortunately, you may not always be able to achieve it.
I
Yes?
have a question. Sir, in the second property, like the B resource, both of them have same, like, red also values it by 1 unit and blue also is valuing 1 unit.
Yes.
So, ambiguity.
So I'm not comparing it resource by resource. I'm comparing bundles with bundles, or sets of items with sets of items. Right? So what is red's set? Here it's just the singleton set A. What is blue's set? It is B union C, B and C together. So I'm comparing the set A with the set B and C. All good? All right. Okay. So this is maybe one very important limitation of envy-freeness. Another limitation, which kind of is a very computer science-y limitation, is that given as input any such value matrix,
We can check it in forward.
we don't know of any fast algorithm that can quickly tell you if there is an envy-free way of assigning the objects. Yeah? Formally, this problem is what is called an NP-complete problem. Has anyone heard of NP-completeness here? Everyone is familiar with the concept? Yeah? Okay. So it's basically saying it's a hard problem, right? You cannot expect to have fast ways of checking whether there is an envy-free way of dividing stuff. Okay. So this is a very nice notion, but it fails the existence test and it fails the computation test. Okay? All right. So whenever researchers see nice notions that fail, their automatic response is to think of approximations. Okay. So now we are going to lower the benchmark a little bit. Right? Envy-freeness is too strong. Yeah.
Thank you so much for delivering it in a nice manner. I have a doubt.
Yes, please.
The preference and the value of that preference, real-time resource allocation problems.
Yeah.
It need not be a fixed one. It can change actually.
100%.
Preference towards one object can change tomorrow.
100%.
It is not a constant. It is going to be a
True.
dynamic in nature.
True.
How do you consider that?
Yeah, so that's an extremely interesting question. In this presentation, I'm giving you a very, very simple toy model just to get you started on it. But there is research on the problem that you are stating, that sometimes come and go, right? Sometimes even if the resource is the same, your own perception of it might change. You might have valued it a lot yesterday. Today you may not care too much about it, right? Your preferences can improve or become worse.
Multiple agents when they interact.
Yes. So
Multiple agents when they interact and it's a dynamic in nature.
Absolutely,
The problem
absolutely.
is highly complicated.
yes. So
Especially
people.
in complex systems.
Yes.
We need actually a lot of algorithms.
Yes.
Already you talked about the NP complete.
Yes.
So my question is whether people will be preferring actually some approximation and
Yeah. So this is just like I said, just to get us started on thinking about a problem, right? Whenever we start thinking about a problem, we look at a simple model and then add some features to it, right? So this dynamic aspect you are mentioning is something that people do study. I'm not going to go into it too much here, right? But it's very much a topic of active research, right? How do you even define fairness when your value is going up and down? Coming and going.
See, especially applications, it's highly dynamic in nature.
Yes. Yeah, exactly. So these things are, very much objects of current study. Like, I attend a lot of conferences where people write research papers exactly on the problem you're mentioning. So it's not a solved problem. It's like something that we are still figuring out. But there are studies on it. So I'll be happy to point those to you. But I think they are somewhat more sophisticated for me to present them in a short amount of time.
Okay.
Yeah, but very happy to discuss it offline.
Thank you.
Yeah, thank you so much for your question. Any other questions? Okay, all right, cool. So, envy-freeness Very nice notion, but fails to exist, hard to compute and all that. So we are going to lower the benchmark a little bit. We are going to think about approximate envy freeness. Okay? So we are going to, okay, you can tolerate some amount of envy. Okay? Because these are discrete objects, there's got to be some envy. So we'll try to tolerate some of it. Okay? So we are going to define a new notion called envy freeness up to one good, which says that you can eliminate envy. Right? You know, you're looking at two agents. It says that, okay, you are allowed to envy someone else, right? But it should be possible to eliminate the envy by dropping, hypothetically, some item from the other agent's bundle. Okay, let me give you an example to make this clear because it sounds a little bit strange. So suppose again this is my problem instance. Okay, and let's say okay, I'm not saying this is good or bad, I'm saying this is an allocation, let's analyze it. Okay, so item C goes to red, A and B go to blue. Okay, as you can observe, this is not envy free. Why? Because look at red, it's getting a value of 2 for its stuff, and it thinks that blue is getting a value of 5. Right? So it values blue stuff more than its own stuff, so it envies blue. This is not envy free. Okay, there is envy here. Okay? But now red agent is doing this thought experiment. It's thinking that, okay, I envy blue, fine. But what if I hypothetically, you know, in an imaginary manner, drop this item A from blue's bundle. Suppose blue did not get item A, just as a thought experiment. Then I will not envy blue, right? Because then I'll compare 2 with 1 and I'm happy. So red envies blue up to the removal, hypothetical removal of one of the items of blue's bundle. Yeah? Okay. Similarly, look at blue. Blue envies red. Yes? But it would not envy red up to the removal of some item from red's bundle. Yeah, again, blue is doing this thought experiment. We are not actually throwing away anything. We're just telling ourselves this story in our heads. Right? So basically, agents envy each other up to one item. We are just telling them, hey, if this other agent did not get this one item, I will not envy them. So my envy is bounded by just one item. Right? That's the sense in which it's approximately envy-free. Okay? So this is the sense of approximation here. This is just a definition of approximation. I'm sure more definitions are popping up in your heads right now, right? Which is completely fine. This is just one way of defining approximation. I'm not saying this is the only way. Okay? There can be other ways, and we can talk about those later. Okay? But anyway, so basically, this notion, which is called EF1, envy-free up to one good, it's very much like envy-freeness, right? So if you look at the math formulation, agent I is comparing its value for its bundle with its value for any other agent K's bundle, but you are now allowed to drop some item in agent K's bundle. So we are asking that for every pair of agents I and K, there should exist some item, say J, which if you remove from the other bundle, you will not envy the rest. Yeah? Okay? So it's envy-free up to some degree. Okay? Now, why am I so excited about this EF1 notion? It's because it fixes the two limitations of envy-freeness from the previous slide. Right? I'll show to you that EF1 actually is guaranteed to exist, no matter how many agents, no matter how many items, no matter what these numbers are. I'll give you a very simple algorithm. I'll give you a proof that no matter what input you're given, EF1 always exists, and in fact, you can find it efficiently. In polynomial time, you can find it. Okay? Yeah? Everyone ready to see the proof? Yeah? Okay. So it's actually a very simple algorithm that does it. It's called the round-robin algorithm. Probably you have heard of it or come across it in some context or the other, right? Basically, let's order the agents from 1 to n, give them names, 1, 2, 3 up to n, and let them take turns in picking the items. Okay, so first agent 1 picks, then 2, then 3, go all the way to n, right? In every turn, everyone picks their favorite remaining item, a single item. Okay? When you have exhausted the n agents, restart from agent 1. 1, 2, 3 up to n, 1, 2, 3 up to n, 1, 2, 3 up to n. Every time one agent picks their favorite remaining item, at some point you run out of items. Okay? That's the algorithm. Okay? So let's do an example. This is, suppose 3 agents, 5 items. Suppose red goes first. Its favorite among these is A. Yeah, it takes that. Then blue goes next, is favorite among the rest is C. Okay? Now green goes, what should green pick? So green, what does green see? It sees B, D, and E. They're all value 1, pick anything, right? In my slides I'm picking E, whatever, and then
D.
then red goes,
D.
right? Red picks what?
D.
Red picks D, because it sees B and D, D is better, it picks D. Poor blue agent, it has to pick the last item which is worthless to it, but you know, so is life, so what can you do? Alright, does that make sense? Alright, cool. So here comes the proof, here's the theorem that this algorithm always gives you an EF1 allocation. Okay? Let me give you a very quick picture proof, right? Hopefully it conveys the idea. So again, just to remind you how this algorithm works, you have these n agents, A1 to AN. In the first round, everyone is going to pick an item, right? You exhaust n agents, and then second round, 1 to 3, and so on, so on, so on. Last round, you know, maybe you run out of items, right? So some agents get items, others don't, whatever. Alright, so this is the execution of the algorithm. Now, why is it EF1? It's EF1 because of the following reason. You pick any pair of agents. Remember, NV freeness or EF1, they were all pairwise properties. Fix your favorite pair of agents. Let's call them red agent and blue agent, R and B. And let's just analyze the NV of red towards blue. That suffices, right? If I can prove to you that this NV is bounded, we are done. Okay? So two cases, either red is before blue in the ordering or it's after blue. Okay, so suppose it's before blue. Yeah? So in every round, red picks before blue. Right? So would that arrangement be EF1?
Yes.
Why?
It chooses the best, comparatively chooses the best every time. So
Comparative chooses the best every time, right? So round by round, item for item, red likes its own bundle better than blue. Why? Because, you know, at this stage, this item and that item, they were both on the table, but red chose this item. So it must like that one. In this round, they were both on the table, but red chose this item over that, so it must prefer that item over blue's item. Yeah? So item for item, red prefers its bundle over blue's bundle. Yeah? Okay? Now in the last round, I don't know, maybe blue gets an item, maybe it doesn't, I don't know, but doesn't matter. Okay? What you can see is that because item for item, red prefers its own bundle, by additivity property of sets of items, it prefers the entire bundle over blue's entire bundle. Yeah? So we are using additivity here. Right? This is why we assumed it before. All good? Right? So what you are actually seeing is that not only am I proving EF1, I am proving NV free here. Anytime you pick before someone in the ordering, you actually don't envy them at all. Forget EF1, it's NV free from your perspective. So it's a stronger claim. Yeah? Excellent. So what should I do next? Is the proof over?
No, we should have
The other case remains, right? So let's analyze that. Okay, so now blue comes before red. That's the other case. Right? Okay, so what do we do here?
we should prove at least a red disk and EF1.
How do I do it? Any quick thoughts?
If we remove the first rounds B,
Excellent, excellent. So let's call blue's first item G, good G, and observe that when it is red's turn here, this item and blue's next round item, they are both on the table, but red chose this one instead of that, so it must weakly prefer that. So this time arrows go downwards. Yeah? What does that mean? It means that except for this item G, item for item, red prefers its bundle over blue's remaining bundle. Except for the item G. If you drop it, then item for item, red prefers its bundle over blue. Right? Does it remind you of something?
EF1.
EF1, that's exactly EF1, right? So by additivity, again, you can say that red prefers its bundle over blue's bundle minus the item G. QED, that's the proof. Yeah? Simple enough? Okay? So what I've shown to you is that no matter what references you're given, you can always find an approximately NV free and approximately fair allocation using a very, very simple and intuitive algorithm. Yeah? Okay, cool. So EF1 is good, but it actually also has some limitations. It has some downsides. You know, not all is rosy with EF1. What is a downside? Well, suppose there are these two agents, yeah, and you have these resources. There are 3 resources. There are 2 donuts, which are okay. I mean, I like donuts, but not more than a very expensive car, right? And I'm sure pretty much everyone in the room thinks that this is a very, very valuable resource compared to these. No offense to donuts, I like them, but I mean, car wins, okay? Okay. So suppose I divide the resources in this way, yeah? I claim that this is EF1. Yes? Right? Why? Because sure, red is unhappy, but if you remove the car, it's not going to envy blue, right?
Yeah.
Okay? So this is EF1, but not a very satisfactory allocation, right? You would be very unhappy allocating stuff this way, right? So what is a better way here?
Split the car into 2, just kidding.
Sell the car.
Sell the car. Well, no, let's say
Both of
we.
their choices.
Pardon me?
Removing car out of both of their choices.
Well, let's say we have to allocate these stuff, right? So we can't blow up the car or anything. Okay. How do I allocate these resources?
Is it a single allocation, like if B gets the car, A can't have at any point of time at all?
Yeah, these are, yeah, exactly. I mean, the car has to go to one person or the other. Do you see a slightly better way of allocating stuff here?
At least you
Please
don't
take
have to
donuts.
be.
Exactly, right? A is having a very hard time here. At least give them a donut to conquer their, worry and sorrow. Right? So this is probably a less bad, less hurtful allocation of these resources. Okay? Alright. Okay. So this brings me to another fairness notion called envy fairness up to n equal, which is like a stronger, more powerful cousin of EF1. Okay? So this is called EFX also, and what is this notion? It says that, remember in EF1, I demanded that you can remove envy by dropping some item. Right? Now, in my previous example, that some item ended up being a very valuable item, so you're destroying almost the entire value in the other person's bundle. This notion says you should be able to get rid of envy by removing every single individual item. No matter which item is removed, you should get rid of the envy. Okay, so it's a stronger demand. It's a stronger notion. Okay? So here is an example. The red agent here is getting 5. It thinks blue is getting 6. No matter which item you drop individually, it would stop in being blue. Similarly, blue is getting 2 here. It thinks red is getting 2 here, so it does not envy, right? So this is an example of an EFX allocation, a boring example perhaps. The more important thing to note for you is that I'm using the for every quantifier here. Okay, in EF1, it was a there exists some good quantifier. I've changed the quantifier from there exists to for every. That is the only difference between the previous notion EF1 and this new notion EFX. Okay? And convince yourselves that if I give you an allocation which is EFX, it's obviously EF1. It's a stronger notion. Yeah? Okay. So I told you I'm going to give you a puzzle, and here is my puzzle for you. Can you give me a mathematical proof that no matter what input instance I give you, how many agents, how many items, whatever preferences, there always exists an EFX allocation. Okay? So I told you previously that EF1 always exists, right? I gave you a weaker guarantee, and this is my challenge problem to all of you. Can someone here prove to me that an EFX allocation also always exists? Okay? This is one of the big open problems in the area, and I encourage you to think about it because it's a very cute problem, very easy to understand, very easy to state, right? And if you have any thoughts, any solutions, you should reach out to me. I'll give you my email in just a second. Okay? Is the problem clear to everyone? Yeah? Okay? Alright. So just to wrap up, this idea of fairly allocating resources is part of this broader area called computational social choice, right? Which I briefly mentioned to you that it's about making collective decisions, right? And fair division is also about making collective decisions, right? Because those preferences, those numbers in the matrix, they are your preferences. And when I say I'm dividing resources, I'm making a collective decision, a partition for the society, right? So in this case, an allocation is a collective decision. And what we seek in this field is to come up with divisions which have some provable mathematical properties, such as envy-freeness and its relaxations. along with some nice computational properties, like polynomial time computation. Right? So we are seeking some economic properties along with algorithmic properties. And this is the coming together of economics and computer science in these very relevant real world problems. Okay? So this area of computational social choice, or CompSoc as it is called for short, is at the intersection of these three very beautiful disciplines: theoretical computer science, economics, and also artificial intelligence, because preferences play a big role. And the three sort of major problems that one studies in this area are voting, which I very briefly mentioned at the beginning, matching, which I didn't have much time to go into, but it's a very important problem in this area, and fair division, which is something that we just saw. And each of these pillars has tons and tons and tons of real world applications. Okay, they are extremely practical, all of them. Voting, of course, we think of it in the context of political elections, but voting algorithms, right, study of voting procedures is also very relevant when it comes to recommendation systems, right? Amazon and Netflix, etc. They say, you might also like to watch this movie. You might also like to buy this product. All of those are based on study of voting rules, right? Under the carpet, they're all doing voting computation, right? Matching problems, you all, I'm guessing, familiar with, booking cab rides, that is a very important real-world matching problem. Matching students with schools. One very important application of matching algorithm is matching organ donors with patients, right? So sometimes, just to give you a very quick example, I'm about to wrap up. Suppose you have a pair of family members, right? And let's say one family member is in need of an organ, and the other one is willing to donate to them, but cannot because of some medical issue. Right? So there is a willing but incompatible organ donor. Right? In this pink case, for example, the mother wants to donate to her daughter but cannot because of whatever medical reason, say blood type mismatch or whatever. Yeah? Similarly, there could be another such pair of willing but incompatible father and son pair. Yeah? But often it happens that they are cross-compatible. So the donor of one can give the organ to the other, and donor of here can, this one can give the organ to the other one. So if you think about this pair as a node in a graph, think of this pair as a node in a graph, what you're doing is basically a matching, right? If you think of organ possibilities as edges of the graph. So this is nothing but the matching problem that you have probably studied in your discrete math or algorithms courses or other courses. This is actually being applied in the real world to literally save lives, right? And these kind of contributions actually won the Nobel Prize in Economics in 2012. So these are like really, really significant problems, okay? And finally, we talked about fair division, which has again many applications, spreading inheritance property, allocating public housing units, giving out courses, so PSG, I'm sure, faces this trouble where they have to figure out, okay, who gets which seat in which course, right? It shouldn't be that the senior students have all the fun, the junior students should also get their preferred courses, right? So they have to be fair in dividing those resources, right? So this is a very real world problem, fairly allocating stuff amid all the constraints and such, okay? So just want to conclude, anyone wants to get in touch, this is my website, that's my email. If you're interested in applying for PhD positions at IIT Delhi, please get in touch. And yeah, thank you so much for your attention. Yeah, happy to get started. Any quick questions? Everyone looking forward to dinner, I suppose? All right, okay.
See whether the agents can interact with each other.
Yeah.
When you are dealing with multiple agents,
Yes.
so they will be interacting with each other.
Yeah.
So some protocols should be there, communication protocols.
Yes, yes.
What about the security of that communication protocols?
Right, exactly. Again, very good question. This is not something that I study here, right? So I am sort of abstracting away from the communication. Communication complexity, security, and those kind of topics. Not something that I study, but again, I mean, I can share some pointers on that literature, but it's not slightly different from my research area.
But thank you. But see, in the real-time applications, when you want to your research, so it has to be integrated with all the security aspects and.
Yes, yes. So I'm by no means saying that, you know, if you just develop algorithms for these EF1, EFX, you can just apply them as is. Of course, algorithms are situated in a context, right? You have to understand that, you know, algorithms, the data is coming from real people who may have their own incentives. So we have to design the algorithms keeping into consideration those incentives and communication channels and all those things. So there's a lot that goes on top of these algorithms, but I think these algorithms are at the very core, the foundational level of all of these problems. So I think it does make sense to study.
Yeah, thank you so much for your nice presentation. Easily everybody could understand actually the concepts, and for the students and other researchers, I think a lot of openings are there.
Thank you.
Thanks a lot.
Thanks a lot.
Classmates algorithm படிங்க இன்னும்
Thank you so much. Thank you all.
So due to lack of time, we are not having this interaction session, so speakers, they will be open for their questions, so please keep in touch with them through things. So a quick vote of thanks. So good evening to everyone. So it's the honor and privilege to thank our speakers. Professor Shaprava Nath from IIT Bombay and Professor Rohit Vaish from IIT Delhi for enlightening us with their insights on how these decisions from multiple individuals can be treated effectively and fairly, and how each individual will be getting their own good share of the allocation. So it was a very nice and interesting talk. Hope these topics will trigger some of our young minds and motivate them towards the research. And I take this opportunity to thank our management, PSG College of Technology and our principal for always encouraging and supporting to bringing great talents to our campus. And my sincere and heartfelt thanks to our director, Dr. R. Natarajan, who is the driving force and energy behind all the activities. And my heartfelt thanks to our head of the department, who is always there as a pillar of strength and motivation. I wish to place on record a sincere thanks to Dr. Ranga Rajgopal, ACM India, and Dr. Prashant K. Nair, Chairman, ACM Coimbatore Professional Chapter, for coordinating this event. And I extend my sincere thanks to all the members of ACM Coimbatore Chapter who are all listening through the streaming. And a sincere thanks to a special invitee, Dr. R. Anita, visiting professor, for her valuable presence. And my heartfelt thanks to the senior faculty member R.S. Lakshmi and Gauri Shankar for attending this event, and also students who have gathered in larger number in spite of this extended timeline. So thank you so much, and I invite you all for the dinner. Thank you.
I have only one. There is an English say, a journey of 1,000 miles started with a single step. I think this is the first time they have stepped into PSG College of Technology. Let us give a big clap. And the subsequent message is principles of locality, right? It should be a temporal locality. The subsequent visit, always we look for. Thank you so much.
Thank you so much.
And thanks for your active participation. Now let us adjourn for dinner.